Okay, so we're doing the M1 IAL Edexcel paper in this video. So we're doing the M1 June 2017 IAL Edexcel paper. First question is a statics question with three forces. I'm going to do it in the standard way first, but because there's only three forces, there are alternatives which can be a little bit quicker and quite nice to see. But let's do it the way most people would do this, because this is a more general method where, you know, if there were more than three forces, you'd have to do anyway. Anyway, so we've got the diagram here. Let's mark on some forces. That's the F, that's the T, which we're being asked to find out. Because of this angle of 40 degrees, we've got an angle of 40 degrees here, and we've got an angle of 30 degrees here. So if we look at the resolving horizontally, then we need the components of F which are horizontal and the components of T that's horizontal, and the 5 Newton force is acting vertically, so that won't come into this equation. So if we look at this component here, that's going to be F cos 30, because it's next to the angle that we've marked 30 degrees on the diagram there. And the component of the T force going in the opposite direction horizontally will be T sine 40, because that's away from the angle 40 degrees that we've marked on there. Okay, so let's write that equation. F cos 30 is equal to T sine 40. They're going, both those are horizontal components going in the opposite direction. Okay, so now let's resolve vertically. Looking at the vertical components, you've got the component of T vertically is T cos 40, because it's next to the angle 40 that we've marked there. And this force here, the F, will be F sine 40, because it's away from sine 30, so to say, because it's away from the angle of 30 degrees which I've marked on the diagram there. So we have the two forces vertically, which go T cos 40 upwards plus the F sine 30 upwards is equal to the 5 Newton force going downwards. Let's not put units in equations, equals to the 5. So we have basically simultaneous equation which we can solve by substitution. Ask for T first, so let's substitute for F. F is equal to T sine 40 over cos 30. So we're going to substitute for F. Let's go over here, substitute for F, which will be T cos 40 there, plus F, which we're going to substitute T sine 40 over cos 30, equals to times by sine 30 equals to 5. Okay, right, so we can work that out using our calculator reasonably easily. I'm going to just do a little bit of trick, but as long as you can use a calculator effectively, that should be pretty straightforward from here. Sine, because we've got sine 30 over cos 30, I'm going to write that as tan 30 equals 5. And then we have T cos 40 plus sine 40 tan 30 equals 5. So T is equal to 5 over cos 40 plus tan 30 sine 40, which to three significant figures never give more than 3. You can do 2 here. Well, maybe not, because we haven't used G, so you give 3 significant figures, 4.40 newtons. Okay, that's T for part 1, and then part 2, just now we know T, we can put that back into F. So F is equal to that 4.40, which I've got stored in the calculator, the exact bit, times by sine 40 over cos 30, which is equal to 3.26 newtons. Okay, so now to the alternatives, which are quite nice when there's free forces to use these, but only really if you are totally confident with your mechanics. This will save you time if you're confident, but don't ever try and think of using these methods in most questions, because most questions have more than 3 forces. Most statics questions won't work normally, but work here and you can save a bit of time. First way is triangle of forces. So we draw these forces in a triangle. We've got the F, which is going upwards like that, 30 degrees. And then the 5 newtons, which is going down like that, 5 newton, and then the T, which is going upwards with that angle as 40 degrees there. Okay, so then if we mark on the forces here, this angle, the angles here, that's 5. This is our, that's 5 newtons. This angle here must be 60 degrees because of the right angle here. This angle here, because it's 40 degrees here, would have to be 50 here. Okay, so then we, so basically that means the whole of this angle here, replace that now, is equal to 80 degrees. Okay, and this is the force F, as I've said, and this is the force T, and then we could just use the sine rule. So triangle of forces only works with 3 forces, it's sometimes called a 3-force diagram. Sine of, let's do it the other way around, F over the sine of 40 equals to T over the sine of 60, which is equal to 5 over the sine of 80. And then we can get F and T very quickly from that, because we can say that F equals to, let's get T first, because the rest for T, using this bit here, is equal to 5 sine 80 times sine 60 equals to 4.40, which we've already seen, of course, we know what the answer is, and F equals to 5 sine 80 times by sine 60, or sine 40, sorry, that's this bit here times that, which is equal to 3.26 newtons. So let's draw in a triangle of forces diagram, which is you know, a little bit quicker, but it does involve drawing a triangle, and some people don't like doing that, and they prefer to stick with this method, which is a general method, the original for everything. There's even a quicker way using a kind of old traditional theorem named after a French mathematician called Lamy's theorem, which actually amounts to the same thing, but I'm going to do it that way since we're going to go to town on this question a little bit. I imagine most people aren't even listening to this, because they probably fast forwarded it thinking I'm going to do it the normal way. Never mind, I just think it's quite nice. So Lamy's theorem, and what Lamy's theorem says, basically if you have 3 forces, F1, F2 and F3, then the ratios, and we mark these forces here, alpha, beta and gamma. The Lami's theorem is basically saying that the ratios are the same with the, that should be a gamma there, it looks a bit like an alpha anyway. The ratios of the angle opposite with the force are the same. So in other words, F1 over sine alpha is equal to F2, looking opposite there is sine beta, which is equal to F3 sine gamma. Okay, so then what we do, if we actually do this on this diagram here, and we look at what the forces are, let's redraw the diagram over here. We've got the 5 Newton force downwards, we've got the F going upwards, and we've got the T going there. If we mark the angles on here, that angle's 30 degrees, so this angle here is equal to 120 degrees. Okay, this angle here, because that angle is 90, this angle here, that angle's 90, this angle here is equal to 50, so this angle here is 140 degrees, and then this angle here is 40 plus 60, which is 100 degrees, and then that's F and 5 and T. And then what Lamy, if we put this into Lamy's theorem, we'll get that F over the sine of the angle opposite equals to T over the sine of the angle opposite equals to 5 over sine 100. Notice it looks very similar to the sine rule we use. We would have had sine 40 here when we use a triangle, and we would have had sine 60 here. Of course it's the same thing, and we would have had sine 80 here when we use the vector triangle, which amounts to the same thing. So then that gets us the two angles that we want as well, the two forces we want. If we want T is equal to 5 over sine 100 times sine 120, which is equal to 4.40, and F is equal to 5 over sine 100 sine 140, which is equal to 3.26 newtons. Okay, take that if you want it. This would save a bit of time, but only works for free forces. Either way, Lamy's theorem. Okay, let's have a look at question 2. So question 2 is a moments question with a uniform. Look for the word uniform rod, being modelled as a uniform rod. That's the first thing to look for. This one is of length 2A, and we're being asked to find A. But what we do know is that the centre of mass of the rod, or the weight, comes forth as a single weight in the middle of that distance there, where this distance from here to here is A. Okay, we're told what the reaction force is here, which is 120 newtons, and we're also told that there's a weight of 30 newtons downwards there. There's something resting on it. We don't know R, but we don't know, we're not told the reaction there, so it makes good sense to take moments about C, because then R won't go into the equation. Let's mark on some distances. This distance here will be equal to, because as I just said, that the length is A to the centre of mass of the rod, so this distance here will be A minus 2. Okay, and then obviously this distance here will be equal to 4, because it's the difference between 6 and 2. And the length from here to here, because again we don't know the length of the rod, will be 2a minus 2. So we can do that, use that to write a moment's equation about C. Right, now the 120 force is going anti-clockwise, it's going in this direction upwards. So let's 120 times 4, that's the anti-clockwise force, is equal to the moment of the two clockwise ones, force times distance, a minus 2 times 140 plus, and the length of this 30 times 2a minus 2. So multiplying this out, or well, we can knock off a 0 I suppose, then multiply out 48 equals to 14a minus 28 plus 6a minus 6. So rearranging that, I get 20a equals to minus 34 plus 48, which is 82. So a is equal to 82 divided 20, which is 4.1 newtons. Okay, so that's part A done. So part B, what's happening is they're moving this support. So let's redraw the diagram. Let's put it over here. The new distance E. And what else we're told? We're told that now the reactions are the same at the two supports. Okay. We've still got a weight of 30 newtons here. And we now know that A is equal to 8.1. So 2A is equal to 4.1, so the length of the rod is 8.2. Okay, so we've got the weight of the rod in the middle, 140 N. Okay, and we're being asked for the length AE. Let's mark that length X there. We're being asked for that length there, X. Okay, well we can work out the reaction quickly enough. That's probably a good idea because we really do need to know what that reaction is. Resolve vertically, forces up equal forces look down. So we have 2R is equal to 140 plus 30. So R equals to 85 newtons. Now that makes everything nice and straightforward now, because we can just do a moment's equation to work out X. Now I'm going to take moments about A. I know it involves more forces. Normally I say take a moment about a support, which eliminates one of the forces. It just to me it's just as easy, even though you've got 4 forces in the moment's equation, at least X will come into the equation directly without need for brackets and things. So I might prefer to take moments about A here. So we mark on the distances. The length AC there, that's equal to 2. The length there, we now know that's what the A was that we've worked out before, so that equals to 4.1. This, as we said, is our unknown distance, so we've been asked for X, and this obviously is the total length of the rod, which is 8.2. And so we can set up a moment's equation from that. Okay, the two anti-clockwise ones are the reaction forces, R times 2, I know we know R is 85, but let's write R for the moment, plus R times X, Rx is equal to the 140 times 4.1 plus 30 times 30 times 8.2. Right, now here we have r time. We know that r equals 85, so this would here would be 170 plus 85x is equal to 140 times 4.1, so plus 30 times 8.2, that comes to 820. So 85x is equal to 650. So x is equal to 7.64. Yeah, so 7.64 meters. Don't normally penalise in M1 for lack of units, but I better put them in there just in case. Well, strange enough, I put newtons on there, which really needs to go because it's not a. Be meters. You wouldn't be penalised for that, but it's a bit silly. Anyway, let's get on to the next question and see what we can score there on question 3. Okay, so question 3 is an impulse and momentum question. The main thing with these questions, particularly with impulse, where you have to use input, is to get the signs correct. We've got two particles, P and Q, and they're coming towards each other, and they've got mass 0.5 and m, unknown mass, and they're coming towards each other. We're given the speed of P is 4 and the speed of Q is 2, and we're told that the magnitude of impulse, so when they're actually colliding, there's an impulse on P of 4.2 in that direction, or minus 4.2 or whatever, and an impulse on Q of 4.2 in that direction during the impact. But then we're told that the direction of P is reversed. Okay, it's reversed, and let's call it V. And the direction of Q may be, well, but that's talking about the second part, may be reversed or it might not be, depending on the scenario. So let's leave that for the moment. Now we can't use impulse on Q because we don't know the mass. We can't use momentum, the conservation of momentum generally, because we don't know the mass and either. So we need to do the impulse equation. There really is no way around this on P, so it's kind of forcing us to do it. Normally momentum's an easier equation to use, but we're really forced to use the impulse equation on P here because Q has got an m in it and we can't really, we've got two unknowns. Right, so we've got to be very careful. These questions, you've got to be very careful about the signs. So if I'm going to actually call this way positive, because otherwise there's lots of negatives going on, because the impulse is actually in this direction. So, and the impulse equation goes I is equal to mv minus u, if I write it in factorised form like that. So because I'm going to take this direction is positive, that means this is 4.2 equals to the mass, which is equal to 0.5 kilograms, times by V. Now we're told that V reverses. We know that V reverses, so that's positive V. Okay, but we know that U is necessarily going in this direction, which the way we set it up is negative, so it's negative U, or V plus U, which is V plus 4, because of the two negatives cancelling. Okay, so then that gives us V, if we times that by V plus 4 is equal to 8.4, so V is equal to 4.4. Okay, so V is equal to 4.4 meters per second. Okay, so that's part A. That's the had to use momentum, had to use the impulse equation. Part B, it all goes to this thing. We can use momentum now, conservation of linear momentum for part B. And the key to this is that it talks about two possible values of m. Well, we're not told the direction that this goes in. It could go this way, or it could go this way, but we are told it's 1 meters per second. So obviously that scenario will, either one of these cases will give us two different values of m. So let's do conservation of linear momentum. Let's go positive this direction now. That's what we normally do. So force, mass times velocity here, which is 0.5 times 4. Now this is going in the opposite direction, so that's minus 2m, m times 2, is equal to, now this is going in the opposite direction now, so we know that's minus 4.4 times 0.5 for that. Sorry, there's a mistake there, obviously that's 0.5 times 4 is the mass times velocity, that's right, mass times velocity to be consistent, so that's 0.5 times 4.4. Now, we don't know the direction of this one, so to get our two different values, we could write two different equations out, but why not just call it plus or minus 1m, depending on which direction it goes, and that will give us the two values of m that we're looking for. Okay, so 0.5 times 4 is 2, take away 2m, is equal to minus 2.2 plus or minus m. Bringing that all to the other side, we'll get, bring the 2m over there, we'll get 2m plus or minus m is equal to 4.2. So either 3m is equal to, we're taking the positive bit, which is 4.2, so m is equal to 1.4 kilograms, or we're taking the negative one, 2m take away m is equal to 4.2 kilograms, and that's it. So that's how we get the two different values, 4.2 or 1.4. Notice they're both much bigger than the mass of this, which is why the velocity of this one is actually increased from its original one, which had the sense it's going to have to be up against quite a big mass in order to rebound at greater velocity than it actually started with. Okay, so that's question 3 done. There is this question is very similar to one, if you go back to 2002 or 2003, there's a very similar question on an M1 paper there. If you want to have a look at the different, a question, virtually identical question, but with maybe different numbers. So it does go to show that questions do repeat themselves sometimes. Anyway, so let's have a look at question 4. And question 4, I think, is quite a nice, straightforward vertical motion suivant question. What we've done with impulse, but they've asked about impulse again. We've got something that's hitting the floor at 10 meters per second and rebounding at 7 meters per second. So the impulse, which is changing momentum, there are different signs here. It wants a magnitude of an impulse, so I'm just going to make sure it's positive. So we've got mass, which is 0.2 times by 10 plus 7, because they're going in the opposite direction. So that equals to 3.4 Newton seconds. You have to have a positive answer there because it talks about magnitude. So we won't make too much of a fuss of that one. Part B, again, it's pretty straightforward really. It's rebounded with speed 7 meters per second. And we're being asked for the height it would reach. So we can use the fact that V is 0 up there. So we've got U is 7, V is 0, S is we can call it h is the distance it's travelled, and obviously a equals minus g, minus 9.8. So we're looking, the correct equation we're looking for is v squared equals u squared plus 2as. That's the one that involves those three variables. So we have 0 squared is equal to u squared, which is 7 squared, plus 2 times minus 9.8 times by h, which gives me h is equal to 49 over 19.6, which is equal to 2.5 meters. Okay, and then part C, it's so part C, well, it says find the instant it's first 1 meters above the ground. So we've got 1 meter, because what will happen is it goes this, like that. We know it's gone 2.5 meters, and there'll be 2 instances where it's 1 meter above the ground, but it wants the first one where it's 1 meter above the ground. Again, pretty straightforward. We've got u is equal to 7, s is equal to 1, because we want to work out the time, and we've got a is equal to minus 9.8 minus g. So the correct Schubert equation this time is s equals ut plus half at squared. So we have 1 is equal to ut, that's 7t, minus 4.9t squared. Rearranging that, 4.9t squared minus 7t plus 1 equals 0. So using the quadratic formula, t is equal to 7 minus, but we know it's a smaller one. The smaller one will come from the negative, and the bigger, the second time it happens will be the positive. So, but we're being asked for the second one, so it's 7 minus 7 squared minus 4 times 4.9 times 1 over 2 times 4.9, which is 9.8. So that gives us t is equal to 0.16 seconds. Okay, nice easy question that. I'm in the middle of the paper. Let's have a look at the next question 5. Okay, so speed time graph question. This is one of the ones where we've got 2 things moving, and it's important we get the 2 things correct relative to each other as well. So if I draw my axes v and t, let's do that again. V and t. Okay, now we have what we're told here. We're told that the p starts off and moves with constant velocity 10 seconds and a speed up to a speed of 25, and then moves at a constant speed of 25. And then sometime later, 20 seconds later, another train starts off with in the same direction, and it accelerates the same, but it goes up to 40 meters per second. So let's just deal with p first, but I don't want to go too high up because I don't want to use the whole height, because we know that there's going to be another train that's going to go faster. So call that p. It's accelerating up to a speed of 25 meters per second there for 10 seconds. Okay, so that's one. And so it's important we get the other one relative to it correct, because it there says at t20, when after 20 seconds there's another train, and it's with the same direction and the same acceleration, constant acceleration. So it's going to have the same gradient as the one before, and that ends up at 40 meters per second. And then it maintains that speed. Okay, so there's So let's mark that time on there. That's 20. I think that's enough for the 3 marks for our speed time graph question. Label it V and T. Okay, so that's our speed time graph. Then it says find the value of t at the instant when both trains are moving at the same speed. So we want the value of t at that point. Well, it's hopefully we can do it by inspection. We don't really need for calculation because we've got similar triangles here. Yeah, it's the same acceleration. We've got similar triangles, so this would have to be 30. That would have to be 30 there, because the distance from here to here would have to, the time from here to here would have to be the same time because it's accelerating the same. So it's speed as it is for train Q to reach 25 meters per second. So that's got to be 30. Okay. Right, so that's something we've had to work out. So now we need to work out some times. Now, in order to set up our equation, we need to find the time. Let's work this bit out now. We don't really need that on our diagram. We need to find the time that it takes for this one to reach its maximum speed here, 40. There's various ways of doing that, of course. We can use acceleration because we know the acceleration is the same. So acceleration is equal to 2.5 meters per second. And it's gone from 0 to 40. So 40 divided by 2.5. Which is equal to 36, is equal to 16. Okay, 16, and so therefore this down here is that 16 plus 26, plus 16 plus 20, which is 36. Okay, just using acceleration. If you like, we're using v equals u plus at, or we're using a gradient, but the gradient is equal to 2.5, whatever, 2.5, because the gradient of this is 2.5, and this is 40 here, this distance here has got to be 16 here, whatever, so we've got 16. So we need that. The reason we need it is because we need to set up an equation, because it wants the time where they actually pass each other. So that will be sometime later when the areas under the two graphs are the same. Let's call it t. I think it's called t in the question. T. So we need the time when this area here is the same as this area here. So we want that instant when those two are the same. Well, we can set an equation in terms of big T and just equate them. Work out t from that, 8 marks. So it's going to have to do a little work, but I don't think it'll be too bad. So let's deal with p first of all. The area of this triangle here is equal to, I'm just going to split into triangles and rectangles in this case. It's just as easy to do that as trapezium. So half times by 10 times by 25. Plus the area of this rectangle here, which is 25 times t take away 10, because the length from here to here is t take away 10. That's the distance that p has moved, and it's got to be the same distance that q has moved, which is the red area I've marked here. So the area of this triangle, that length is 16, and this is 40, so it's half times 16 times 40, plus, and then this length here is t minus 20, t minus 36, sorry, I need this distance here, sorry, t minus 36, for that rectangle times 40. So multiplying that out, we get 125 plus 25t minus 250 is equal to 320 plus 40t minus 1440. Bringing all those together to the one side, 15t is equal to 995. So t is equal to 66 1/3. Okay to leave like that, or 66.3 if you prefer, for different figures. And that's our answer to question 5. So it's all about setting up that equation properly. Okay, let's have a look at question 6. Okay, question 6 is a reasonably nice vectors questions with i's and j's. We're given a velocity. This is one where we're using v equals u plus at at some point. We're given a velocity, or we're not. We're given an acceleration and initial velocity, and we want to find the velocity, or we'll need to find the velocity after 6 seconds. So we can use v is equal to u plus at to work out the velocity after 6 seconds. So v when t equals 6 will be equal to the initial velocity at the start when t equals 0 plus acceleration, which is minus 2i plus 3j times t, times 6, we know, 6. So that's minus 12 plus 10, so it's minus 2i. And that's 18j plus 4j, so that's plus 22j. And we need that because we want the direction, so it's actually going to be going something like this, upwards, that's north. And we know this distance here is 2 from the minus 2, and the distance here is 22 upwards. Let's do my diagram again, it's a bit messy. That's better. Makes it look like more obviously like a right angle. Right, so we want this is 2 here, and this length here is equal to 22. So we need this angle alpha. So we can work out the bearing once we've done that. Tan alpha is equal to 2 over 22, opposite over adjacent, 2 over 22. So that works out to be about 5 degrees or something like that, we're close to. But anyway, we want the angle here. We want this bearing here. That's 360 take away alpha, and we've worked alpha out to be 5, that's about 5 degrees approximately. So that's equal to 355 degrees. Okay, so that's part A done, and then part B, we're asked for the time it takes to be travelling northeast, that's in that direction. So basically the i's and j's have to be the same, so it's parallel to I plus j, not equal to I plus j, it's basically it's going to be travelling with some constant times I plus j. The key is that the I and j components have to be the same, but we want the time when that happens, so let's use v is equal to u plus at. And we want that to be, let's just work out, u is equal to 10i plus 4j plus acceleration, which is minus 2i plus 3j times t. Let's reorganize that with the t's together. So we've got 10 minus 2t I plus 4 plus 3t j, and because it's parallel to I plus j, you can play around with k's if you want to, but really the key thing here is if it is going to be equal to ki plus kj. So these two are going to be the same. They have to be the same because it's parallel to I plus j. So that's 10 minus 2t is equal to 4 plus 3t. So that's 5t equals to 6. So t is equal to 1.2 seconds. Okay, so that's question 6 done. Nice and easy. Let's have a look at 7. Okay, so this is about finding the resultant of two vectors. We've got the angle between these two is 50 degrees. And basically, we want the resultant, which will be going up there. If you were to draw a parallelogram, a vector, some people talk about parallelograms, some people talk about vector triangles, but the parallelogram will be there. And it says the angle between the direction of P and Q is 50 degrees. Find the resultant of P and Q and the magnitude, and we want to work out an angle. I'm going to draw a triangle. Q is here, and we're told the magnitude of that is 5 newtons. And then P is going up here, and the angle of that, we're told, makes is 50 degrees. And we want the result, and that's of magnitude 8. And we want the resultant. Okay, the magnitude of the resultant there are. So this angle here, we've got a straight line here, is 130 degrees. So we have the magnitude of r squared is equal to this cosine rule, 5 squared plus 8 squared. Take away 2 times 5 times 8, cos 130. That gives us the magnitude of r equals to, not working out, it comes to 140.4 approximately, which gives r squared, so that gives us magnitude of r is equal to 11.9, but that's stored on the calculator. It's not exactly 11.9, but we can store that. Don't use rounded values for the next part. Okay, it's actually particularly important here because the answer is very close to 11. It's only just rounding to 11.9. It's 11.85002147. So it's very important that we store the calculator answer when we use it into the next question, which we will do. So we're going to use the sine rule to work out the angle that we want. Now we actually want this angle on the diagram here. So they're kind of bamboozle us a bit. That's the angle it's been asked for. But we're obviously going to need this angle here. Let's call that angle alpha. And then we can just take it away from 50 degrees to get the angle here, which we've been asked for. Let's call it beta there. Okay, so we've got, using the sine rule, sine alpha over 8 equals to sine 130 over r, which is 11.9, but remember I'm using the 11.85, I'm actually writing 11.85, the actual calculator display, because I get sine alpha is equal to 0.51498 and loads of other stuff. Working the inverse sine of that to 1 nearest the whole number is 31 degrees. So the angle between R and P is equal to, as I said, we've worked this angle out, which is 31, which is 31, so it's equal to 50. Take away 31, which is 19 degrees. Okay, so one more question to go. Question 8. Okay, question 8 is a dynamics question, and yeah, we've got given various things. We're told the coefficient of friction, we're told the angle, and we're given two masses. Let's just draw the diagram. We've got a reaction force up here, and we've got weight here of 2 mg, and we've got the angle alpha there. Now, dealing with the alpha is something I like to do separately. Tan alpha is 3/4, and we can easily verify with a calculator these days, but what we always used to do back in the day was just draw a little 3, 4, 5 triangle, and we can then see that sine alpha is equal to 3/5, and cos alpha is equal to 4/5. Okay, so we can sub those values in for sine alpha and cos alpha when we're setting up our equation. We're being asked for the tension. There's going to be a tension pulling that on there and tension pulling that there. There's another reaction force there. Let's call that RQ, I suppose, to be so that we know they're different. RP. And we've got a weight of mg there, and we've got friction, which is equal, we're told the coefficient of friction is half, so it's half RQ. Right, so let's set up our equations on both of them. F equals 2ma. We have on the Q1, the easier one, that's T minus half RQ equals to mass times acceleration, but RQ of course is equal to just these two are balanced, so RQ is equal to mg, so we might as well write that. T minus half mg equals to ma. That's for particle Q, and then for particle P we've got the component of the weight down the slope, which is 2 mg sine alpha. I'm not going to sub in the 3/5 just yet. Take away T. Now I think we're told it's smooth, so there's no friction on this one. So take away T is equal to 2 ma. So we know that, well, now we can sub in the 3/5 there, so 2 mg times by 3/5 minus T is equal to 2 ma. So that's 6 mg over 5 minus T is equal to 2 ma. Okay, so then I'm going to add these two equations here, this one and this one. So adding, I get 6 mg over 5. Take away T plus T, so that cancels. Take away half mg is equal to 3 ma. That then gives me the, well, I can add those two together, 6/5 minus a half, this is 12/10, take away 5/10, so that's 7/10 mg is equal to 3 ma. Could have cancelled the m before, I suppose, but we can cancel it now. So we have A is equal to 7/30 g. So that's the first part done. Once we've got the first part done, it should be pretty easy to do the second part, because we just put 7/30 back into this equation here. So sub back. We've got T equals to the half mg plus m times by 7/30 g. So taking 30 out as a factor there, we've got, that's 15 mg over 30 plus 7 over 30 mg. So that equals 22 over 30 mg, which is 11 over 15 mg. Okay, 10 marks, not too bad. Quite often see that type of thing. It says, and then it says, for part B, that suppose it's not in equilibrium, suppose it's not moving and it's in equilibrium, it's actually at rest. Find the smallest possible value of mu. So in other words, for some value of mu greater than half, obviously, the thing will be in equilibrium. The smallest value it will be when equilibrium is limited. So there will be some value of mu where basically it's so rough it won't move. So the smallest bit will be when it's just on the point of mu. So we can just consider that, consider this value. Okay, so we're going to say this time there's no motion, so no acceleration. We've got t is equal to 2 mg sine alpha. We've all been parallel for that one. But we've also got t, let's call it mu r, t equals mu r, which of course is equal to mu mg. So we can substitute for the two. So we have mu mg is equal to 2 mg sine alpha. Obviously m and g cancels, and sine alpha is 3 over 5. So we have mu is equal to 2 times by 3 over 5, which is 1.2, quite large. So mu is 1, so that's the smallest possible. The marks you will see virtually inequality for it, but it's just you do get credit as long as you explain yourself. You'll certainly get credit for saying, well, it's in limiting at the point where it's in a limiting equilibrium. That will be the least value of mu for which it is at rest. Just quick before we go, 1.2 for the value of mu. My old maths teacher would have said that's impossible, but apparently I found out some years later that values of mu greater than 1 are possible, but I think perhaps maybe the first time I've actually seen it on a paper where a value of mu is greater than 1 as an answer. Okay, so that's the paper done. Hope you found it useful, and goodbye.